So yeah, thinking about philosophy of quantum gravity and the different things we can do with philosophy of quantum gravity. So I quite liked that the summer school is about the epistemology of quantum gravity, because I think a lot of the focus recently has been on the metaphysics. So I'll say a bit about each of these fields. So the metaphysics of quantum gravity, where we're asking questions looking at the various approaches to quantum gravity, asking what do they tell us about what exists, the ontology. So these different approaches, what do they suggest about the fundamental nature of space-time? Maybe it doesn't exist fundamentally, in which case we need some way of understanding how space-time emerges, because of course space-time exists according to our best current theories of physics. It's a very useful concept, so I believe it exists at some level, even if it's not fundamental. So this is a very interesting question. It's what I looked at for my PhD, the emergence of space-time. We can also ask questions about black holes and Hawking radiation, so what's going on here. So these are all metaphysical questions, and of course about the beginning of the universe, fundamental questions in cosmology. And yeah, I think these are super cool questions, and there's a lot of work going on with these. So I started doing my PhD exploring. And then after a while, after I finished the PhD, I started to have a bit of an existential crisis, as we all do. Probably happens during your PhD as well. So just a bit of a warning if you are PhD students. Because, of course, trying to do metaphysics of quantum gravity is really, really difficult. Firstly, well, we don't have a theory. We've got these different approaches towards finding a theory. They're all doing different things, and none of them are, really fully complete. They're all very speculative, and we don't know if any of these are going to ultimately turn out to be correct. So I was thinking, what the hell am I doing now? I'm trying to figure out the fundamental nature of space and time, but there's not much of a foothold, asking about these theories. So then I think kind of looking at perhaps the metaphysics of quantum gravity, it's fun, it's interesting, but you might turn out to just be completely wrong. And I guess that's a danger with any sort of metaphysics, to be honest, right? So that's the metaphysical questions. But then, of course, we have these other types of questions about scientific methodology and epistemology of quantum gravity. And I think actually originally the philosophy of quantum gravity was focused on these questions. So questions like, is quantum gravity scientific? How do we go about developing a theory? How can we assess these different approaches? What are we actually doing with it? And of course, like I said, these really started off in the context of string theory around 2006 with these two books that were very controversial, taking aim at string theory as this dominant paradigm. Is it scientific? Are they completely off the rails? Are they justified in having all these resources thrown at them? Peter Voigt, put this very forcefully. It's not even wrong. This theory is so far off the rails. And then, of course, Rickard comes along, 2013, arguing here's how we can make sense of it as a scientific framework, and here's how we can assess it, using different tools, but still it is a scientific program. And I've been heavily influenced by Rickard's work. I think it's fantastic. So again, looking at these methodological questions. And then 2019, this workshop, Why Trust a Theory, asking exactly these sorts of questions. So yeah, these questions, is it scientific, developing a theory, and assessing various approaches. So me, following on from my existential crisis, I thought it's nice to move into these sorts of questions, but even more forcefully, what are we even doing with quantum gravity? Why are we looking for it in the first place? What is it supposed to be doing for us? So then I wrote my own little book, which has just come out earlier this year, 2025, Yeah, so I started it kind of just after the PhD. It's taken me a long time to write this, but it's just because I'm slow writing. It's, yeah, quite a short book, 60 pages for Cambridge Elements, and it's meant to be quite introductory, and what I'll be saying today and a bit more will be based on this. Good. And I think I've sent the link, so you should all be able to have a read of this as well. Good. So yeah, I'm still working on curing the existential crisis. The book has started to help me with this, but I think what I'm trying to do in this book is kind of motivate these questions a bit more. And I don't really go about answering the question about why do we want a theory of quantum gravity. I put forward kind of different reasons why we might be looking for the theory. But the next step is to then evaluate these reasons and see what we can do with them. So I hope it's motivational for you. So what is the problem of quantum gravity? That's originally the title I wanted for the book. It got changed, as you can see, because I think the problem of quantum gravity, well, there's a lot of problems of quantum gravity, so it was going to be a lot longer book. So I focused instead on the motivations for the theory. But I think this question, what is the problem, is also very interesting, right? And we can kind of put it like this. Well, physicists are looking for a new theory of fundamental physics known as quantum gravity. Oh, cool, but it's taking them a really long time, more than 100 years now. So you kind of ask, well, what's taking them so long? What's the problem here? Oh, well, seems like there's no data for them to use in constructing this theory. There's no way to test it. This is the problem, or at least this is kind of the standard story about what the problem is. But of course, we'll come back to discuss possible empirical data. So, and then I think a natural question is that, well, do they even know what they're looking for? Maybe that's why it's taking so long. Without these kind of empirical constraints on it, then how do they know what they're looking for? What is the problem here? So, as I said, normally when physicists are looking for a new theory, it's because of some observed anomaly. You've got your existing theories, and something has popped up. You've observed something that can't be easily explained with your existing theories. Or, on the other hand, your theories have predicted something, and then you've gone out to look for it, and you haven't found it. So there's always a conflict with observation, usually, that's motivating the new theory. It's quite clear with the development of quantum mechanics, of course, with anomalies with the black body radiation spectrum, the photoelectric effect, these sorts of experiments that really prompted the development of a new theory. It's maybe less clear in the case of special relativity, but at least there were empirical experiments here, the Michelson-Morley experiment. But of course, Einstein was also motivated by conflicts with the existing theories themselves and symmetries within them. But still, we had empirical observations. But in quantum gravity, it seems like our current theories work too well, right? General relativity, quantum field theory. There's kind of no empirical anomalies that are thought to necessitate this new theory. So I think this is something we should explore. Why is it that physicists are not really being motivated by any empirical anomalies? Rather, I think this search has been motivated really by conceptual dissatisfaction, philosophical concerns, and theoretical problems in trying to even develop a theory in the first place. So it's kind of non-empirical motivations that have been the driving force, which isn't to say that there aren't some empirical ones as well, just that I think these ones have really been the main push for the theory. So, standard story, yeah, we don't have observed anomalies, we don't have a theory, we have these different approaches. It seems like we don't know what this theory is even supposed to be doing. So instead what we've got are these plurality of approaches, and it seems like they're each doing different things, you know. They're starting off with different assumptions, different aims, they're using different methods, and also because of these different aims, they're adopting different criteria of success. So obviously, string theory is looking for something else than what loop quantum gravity is looking for. And so when they have different criteria of success, it seems like, how do we judge them as even doing the same thing? What makes them all quantum gravity approaches? So lots of different approaches here. And I think the natural question then is kind of, well, what makes these all approaches to quantum gravity? We have this label, quantum gravity, and we've put them all in this box. But what is that? So what is quantum gravity supposed to be? So I've been quite inspired by this quote from Wheeler, who says, "No question about quantum gravity is more difficult than the question, what is the question?" And of course, this reminds us a bit of this, where we have the answer to life, the ultimate answer to everything in the universe, which is 42. So this computer that you've just developed has spent a few thousand years, or more than that, I forget, trying to give you the answer to this ultimate question, and then you get the answer and you're like, oh, what was the question I was looking for? So I feel like this is a bit echoing of this situation. So there you go, yeah. 7.5 million years it took to come up with the answer. So I guess we're, you know, after 100 years, we're okay compared to this kind of length of time, right? So then you have to develop a new computer to figure out what the question was even in the first place. So what is the question? That's what I got stuck with, and you can see again how you end up having a nice existential crisis when pondering this, right? Good. So it happened, so Niels Linnemann and I were writing this paper about UV completion in quantum gravity. And we started off the paper by saying, you know, in quantum gravity, most approaches are striving for UV complete theory. And then we got the reviews back, and the reviewer was just like, what do you mean by quantum gravity? And I'm like, oh, yeah, that's a good question, right? Because obviously, the physicists and whoever's reviewing it, they have their own idea of what quantum gravity is. But of course, we didn't mean to refer to any specific approaches. We wanted this to apply to quantum gravity generally. So we came up with this phrasing. Quantum gravity is whatever theory satisfies the set of principles and constraints that are taken to define the theory of quantum gravity. And we presented this at a conference. Sabine Hossenfelder was there, and she got quite angry with this. And also another physicist in the audience, they saw this and they just started laughing, like, oh, you know, philosophers, bloody philosophers, this is the sort of thing they put up. Like thinking it's just an empty statement, right? It's a tautology, right? But it's not a tautology. This is a meaningful statement. It just remains to be filled in a bit. So, of course, the next step is to figure out what are these principles and constraints. So my strategy with writing this book is to try and think, well, if physicists are all looking for an answer, being the theory itself, and we don't really know what the question is that they're starting off to find the answer for, I think we can look at what they're doing. We can ask them. We can figure out their motivations, ask them, hey, what are you doing? Why are you looking for this theory? And once we get kind of a collection of their motivations, we can start to figure out what the question is. So to look at the motivations that are shared by all approaches in order to define what QG is. But actually, I think I don't mean all approaches here. The motivations I'm going to look at are just going to be any motivations. So it could be particular approaches are motivated by those ones, others are motivated by these ones. But that once we get this whole set of motivations, we can figure out kind of the minimal set that is shared by all the approaches to help define what is even meant by the theory. Okay, so this was the strategy. Step one, let's look at the motivations. And from this, we can work out some minimal definition of quantum gravity, which we can help say, well, these are approaches to quantum gravity that satisfy this motivation. And if they don't satisfy this, then they're just not approaches to quantum gravity. They're doing something else. And step two is then to actually examine these different principles and constraints. We get the motivations, frame them as principles, and then evaluate them. So start thinking, well, why are we being driven by these constraints? What's the philosophical underpinning and the motivations for having these? What's the basis for them? Are they necessary? What are the consequences of adopting these or dropping them, and especially combining, because different principles may come in conflict with one another, and then you have to kind of choose which ones you want to work with. And then kind of step three would be to actually look at the particular approaches and how the principles are being used in each to kind of classify or assess progress. Okay, so any questions so far? Yes, please.
Yeah, to me it sounds like, I'm not sure how to phrase it, I just use this tentatively like a passive approach to motivations, when you like what is out there, and then try to make a list of it and minimize it to the really, the denominator that is shared by everything.
Yes, exactly.
So, I'm sure you've thought about maybe another way to say, you could also do a philosophical work about what a question is, what a quest of a question can be, what the formative aspect of questioning could be in order to transform the motivations in the field for the physicist.
Yes.
There is an experimental motivation in there, you just don't see it. You don't know what you're not looking for.
Yeah.
Spot, so to speak.
Yeah, I like this. This sounds very good. So it's a bit of a descriptive project, but also should be prescriptive as well. Yes, I agree with this. What other comments? Cool. So I'll say a little bit about what I mean by motivations, constraints, and also desiderata. Then I'll say a little bit about the empirical constraints, because as I said, and as we just heard, there might be some empirical constraints. Let's look at these. And then I'll come to what I'm calling the primary motivation for quantum gravity, which is supposed to be this minimal definition. And then I think there are two different ways of approaching this, different main ways of satisfying this primary motivation, which I call the standard perspective of quantization, basically, versus a new framework perspective, and then say a bit about the other motivations for quantum gravity. And that, I think, should be enough for this first part of the talk, at least. But we see how we go. So, motivations, as I said, it's starting off as a descriptive project. So looking at any potential motivations cited by physicists, but also other ones that you can come up with, because different people are motivated by different things. So we can have a big list of motivations. So I have a big list now, and I'm not going to go through all of them in a lot of depth, but I'll come back to discuss a few of these over the next couple of days. So the first one, as I said, this primary motivation, can I move this up a little bit? There you go. It's to have a theory that describes the domains where both general relativity and quantum field theory are supposed to be necessary. So it's not just the domains where they're both applicable, because that should be everywhere, but where we cannot get away with ignoring one or the other. So I think the necessary is important there. And also that this new theory takes into account the lessons of both. So I'll come back to say more about this, but that's, I think, the main motivation here. Next one is the incompatibilities between general relativity and quantum field theory. I think here we want a coherent picture of the world. There's a dissatisfaction between having these two theories that conflict with one another, especially conceptual conflicts, we can say. And when we're trying to bring them together, these inconsistencies appear, so we're dissatisfied with that, and it drives us towards looking for a new theory. Unification, of course, is a big one, but there's different senses of unification or different degrees of unification. A minimal one would be to have GR and quantum theory accounted for by a common framework, a broader theory that encapsulates both. But there's also kind of the strongest sense of unification. So Maudlin here, if you've read his paper on unification, it's very nice. He thinks unification, what we really mean by it is not just that we have a single theory describing these different forces, but that we have a theory that describes these different forces as ultimately being the same force, so the same type of thing. So you can think of this like the unification of space and time to become space-time, or the electromagnetic field is a unification showing that the phenomena stems from a single type of object or force. So this would be more of a full unification, such as what string theory aims to do, or at least is on the way. We also have inconsistencies with semi-classical or other kind of hybrid approaches to quantum gravity. So I think these sorts of motivations arise already after the primary motivation. So once you've taken the step and looking for this new theory, you're realizing that some approaches to this end up with inconsistencies, and it motivates you for a whole new kind of theory rather than just trying to put these two together. So there are some claims that a theory with quantum matter coupled to classical space-time is inconsistent. So it's not able to serve as a full theory of quantum gravity. Probably Eric talked about semi-classical gravity, or is going to. And there's also this claim that perturbative GR, so treating GR in the framework of quantum field theory using perturbative methods, you find it's non-renormalizable, and people claim this is an inconsistency, which is motivating a new theory of quantum gravity. We also have singularity resolution, and I'll say more about this tomorrow. But basically, if we have these singularities in our theories, for instance, the singularities in GR are highly motivational, that our theory is breaking down or contains the seeds of its own destruction thanks to singularities in black holes and the cosmological singularity. So this is taken to motivate a new theory. And less often, but sometimes it pops up, the divergences in quantum field theory can be motivational for seeking a theory that's more fundamental than quantum field theory. And already, quantum field theory you'll think is not fundamental itself, right? Because it is on special relativity and quantum mechanics rather than being general relativity and quantum mechanics. Also, black hole thermodynamics. We want a theory that describes the evolution of black holes and particularly gives us an account of black hole evaporation, as is coming from this black hole thermodynamics. We want a complete cosmology. We want to know what's going on in the very early stages of the universe. We want a theory that solves the cosmological constant problem. So that's a problem, that's an empirical one. The hierarchy problem would like an explanation for why the gravitational force is so weak compared to the other fundamental forces. So again, this one is a motivation. Not everyone treats it as a motivation, but some do, so it's a motivation. And again, it's also an empirical motivation, right? Because we're observing the strength of these forces. And the measurement problem, again, not many people take this as motivational, but some do. And I think maybe we could take it a bit more seriously as a motivation, right? Maybe we could use a fundamental framework that actually explains why this problem arises and deals with it. Problem of becoming in general relativity. So some people are dissatisfied with this kind of block universe picture. They want some sort of becoming. They want some real change, things coming into existence, rather than kind of this static picture. They want to understand how time flows from past to present to future, which at the moment usually gets passed off to not being a physics problem, right? Physics has its picture of time, and the fact that it conflicts with our ordinary understanding of time and experience is not usually taken as a motivation, but it could be. And yeah, any more motivations that would motivate you to be interested in quantum gravity? So yeah, sorry this is really quick, but we'll go into a few of these in more depth. So yeah, one of the reviewers wanted a map, so I tried to make a map. I think we have the primary motivation, and then these other motivations motivate the primary motivation. But also the primary motivation itself can motivate different ways of satisfying it. I'm not really that sure about all the arrows in this. Maybe we can work it out together, but that's the general picture, I think. And especially something you can see like quantization. There's different ways of motivating quantization as kind of a way of satisfying the primary motivation. But we might want quantization for different reasons, such as singularity resolution or unification. So we can examine each of these little arrows, I think, and I haven't done it yet. So hopefully this is motivational for you to have a look about how these fit together and whether they do, in fact, necessitate one another. Are they just different ways of satisfying these? And yeah, maybe whether they're necessary or not. Okay. Any kind of questions on that? Yeah, we'll come back to it anyway, see what you think.
Can you say something more about this box? Inconsistencies or semi-classical hybrid theory?
Oh, yeah. I do have some slides on this, so we might come back to this one, yeah. I don't have slides for all of them, but that one I do, so yeah. Because I think this is quite an interesting picture. Yeah.
Is there some background radiation or isomorphism or representation of the background here in your map? Is this some function?
No. It's just... Yeah. It's just put up there and drawn arrows. No. That would be a nice idea, though. A way of working out how they fit together. Yeah. No. Please.
And that was actually I was going to say the next point because of Hossenfelder, because you mentioned her and the verbal beauty thing, because I think behind many of the points that you have, like the becoming or the hierarchy problem, like you quickly get into kind of like anthropomorphic principles, anthropic principles, or beauty as an aspiration or stuff like that. Why didn't you bring that out in there? Because I think it's interesting to explicitly address that for many people it's like really, it's the beauty of the unification.
Yeah.
Where I think it often makes it easier in an argument to say, okay, yes, you might want it, but what if nature just isn't that beautiful?
Yeah. I really like this suggestion. Yeah, especially as regards unification. So I think this is going to be the next step, and particularly on that one, I'd really like to look into it more. Why are we being driven by it? Yeah, so we might come back to it later this afternoon. We'll see. But yeah, I thought you were going to complain I could have made this more beautiful.
I think sometimes you can be error both ways.
Yeah, I think, yeah, exactly. I think in the actual one I put in the book, I had arrows both ways. Yeah, because obviously unification can go up as well as down, particularly. Yeah, so this is a good point as well. Cool. Yeah, and exactly that. The next step is going to be looking at them and really digging into each of these different principles. So I think this got cut from the book because the reviewers thought it wasn't doing anything, but I find it interesting. Maybe something to explore. Obviously, I didn't use it enough in the actual book, but we can classify the motivations as being internal versus external. And by internal, I mean, we have our theories. They work really, really well, and we have reason, therefore, to trust them, right? And yet they have kind of things within them. So just taken on their own, as they stand, as they're actually used, is there something we're not satisfied about our theories? So that might be, for instance, the space-time singularities as being kind of seeds of its own destruction, or the measurement problem, something that's unsatisfactory with the theory as it actually stands. So I would have thought these sorts of motivations are the stronger ones, right? Because these other ones, the external motivations, are the ones that we're kind of importing on the theories. So they're ones that are coming not from the theory itself, but by, for instance, our own drives for beauty and things like this. The desire for unification, or to have this single picture of the world. And also problems that come about once we already try to put these theories together. So the different approaches, different ways of fitting our theories together, we end up with these theoretical problems, we end up with these conceptual problems. But in a way, they're like problems of our own making. They're not coming from the theories themselves as we know and love them. They're coming from our ways to put them together in different attempts. And I think actually most and the strongest motivations are actually these external ones, which I found kind of interesting. But yeah, I'm not sure I have too much more to say on that. Just something I thought was interesting. So motivations then can do different things, right? If we're going to translate them into principles, well, we can use them either as constraints. So these are principles that the theory must satisfy. Otherwise, we're just not going to accept it as a theory of quantum gravity. And these motivations that serve as constraints might then form part of the definition of the theory itself. On the other hand, motivations could just be heuristic, like guiding principles. So I'm saying they're kind of non-necessary, but it would be nice if the theory had these features, right? So the kind of nice things, or desiderata. So we might start off wanting these things, but seeing where they lead us, and it would be nice if the theory satisfies these, but it's okay if it doesn't at the end of the day. So they might be retained in the theory, or they might not. You might think something like Mach's principle in GR, it's motivational, but whether or not the theory actually satisfies it, less clear. But nevertheless, if it does satisfy these nice things, then it gives us kind of a boost in our credence for it. So the guiding principles, we might think, unification, UV completeness, so that the theory is well defined to arbitrarily high energy scales. It's not breaking down anywhere. We might have particular theoretical problems that we want explained. So this is motivational for us. So we might start off by looking for these and even building our theory to satisfy it. And I think in that case, they can still serve to increase credence in our theory, even if we've set it up wanting to have these. A lot of people find that a bit disagreeable, like it's a bit of double counting, but I never understood why. Maybe some of you can illuminate me on this. But on the other hand, it might turn out that these nice things pop up without us actively searching for them. They might come as a sort of bonus or an unexpected, Rico talks a bit about the expected versus unexpected ones as well. So I think these can also be indicators of non-empirical confirmation or pursuit worthiness. The constraints, as I said, these ones are really the strong ones. We won't accept the theory if it doesn't satisfy these principles. And these ones, they can be motivational, but not all of the constraints on the theory motivate you. But maybe that's debatable. I think, like, for instance, we have symmetries from our current theories, and we don't want to violate these, so that's a constraint, but it's not a motivation to look for a new theory, right? This generalized correspondence principle I always found really interesting. You know, when we develop a new theory, there's a requirement that it explain why its predecessor was so successful in spite of being false. So this is a constraint. A theory won't be accepted if it doesn't have this link back to our current successful theories, approximately in the domains of success where we know they actually apply. So this is a constraint, but I'm not sure it's a motivational constraint. It's not getting you to look for a new theory. It's just saying the new theory needs to satisfy this. And of course, empirical constraints. We don't want our theory to conflict with these. And some of these are motivational, some of them are not. So, yeah, this was me trying to make a little map again. Let's see how it works out. So we can have our motivations. The necessary ones become constraints. The non-necessary ones are desiderata, or the nice things. And if the motivations that we're using, the non-necessary motivations that we're using as guiding principles, they're being used heuristically, we're expecting it, so we're using it, but then they might also pop up unexpectedly and serve to increase credence in our theories, despite us not being motivated by them to begin with. So those are the unexpected ones. And then similarly for the constraints, we have the ones that motivated us to look for the theory in the first place, so they form part of the definition of the theory. And then we also have these constraints that are necessary conditions on our theory, that it must satisfy them, but then not the ones that have motivated us to look to begin with. So that's the picture. That make sense?
Sorry.
Yeah.
There's no motivation that is neither necessary nor not necessary, right?
What do you have in mind?
No, I think you were right.
Oh, so there's nothing in that.
Yeah.
So this part should be empty. Yeah, actually, that's a good point. That's a really good point. Now I want to think of one, but seems like a contradiction there. Cool. All right. I wish you'd told me that before I publish it. So, empirical constraints now. So I think now we've got kind of three groups of empirical constraints of our theories. The first are those empirical stuff that is not explained by current theories. So these are the anomalies. We have empirical constraints that are currently explained by our theories. And then we have future discoveries. So the ones that are not explained by our current theories, I think the biggest ones that stand out are the problems of dark matter and dark energy. So for dark matter, we have these various astrophysical observations that can't be explained by GR and the known amount and type of matter that we think exists in the universe. So we're left with these problems, empirical problems. And yet, these problems of dark matter, they're not usually taken as driving a new theory of quantum gravity. So I think this is pretty interesting. Instead, they're just looking for a new type of matter that we could put into GR and then it would explain. So you're not seeking to replace GR usually with this. It's motivating, some new particles with certain properties, so it's motivating a search that way. Or perhaps it's primordial black holes motivating the search that way. So I think this is quite interesting, It could be a motivation of quantum gravity. Why not? And especially if we had a theory of quantum gravity that naturally solved this problem, would take this as evidence for the theory. So I think this is an interesting question to ask. Of course, there are some approaches that do take it as motivational and do seek to explain it. Same with dark energy, the expansion of the universe is accelerating in a way that can't be accounted for according to our currently accepted pictures of cosmology, which are based on GR and the known amount of matter in the universe. But again, this one is not usually taken as motivation for a new theory of quantum gravity. And it's not usually taken to be related to the problem of dark matter either. But again, it could be quantum gravitational. I just came yesterday from another conference, and I was speaking with Claudia Diram, and she's quite interested in these questions. So if dark energy has something to do with the energy intrinsic to space itself, then it could be telling us about quantum gravitational effects. Okay, so those are the main ones that are not explained by our current theories. I think there are others, as I mentioned. The hierarchy problem, if you're taking that as an empirical problem, in need of an explanation, for instance. Next up, those empirical constraints that are currently explained by our current theories. Again, as I said, these aren't motivational because we don't need a new theory to explain them. We've got our current theories, but it's a constraint. So we don't want our new theory to conflict with what we know about the universe. We want it to match up and be coherent with our current successful theories in their domains of success. And it's quite nice too, because it's also like a shortcut to empirical results. These theories of quantum gravity being developed, they're very, very far away from the domains where we can access, right? So if you can do a nice derivation and show how GR comes out, show how quantum field theory comes out, then you've got a shortcut to empirical results. GR has empirical results, and if you can show that GR is a consequence of your current approach to quantum gravity, then you've got the empirical link there. So that's quite important. And I think that's really the main constraint that everyone agrees upon in quantum gravity. They call it like the 0th constraint. And finally, we have future discoveries. These will be novel empirical results. And some of these are coming about from quantum gravity phenomenology. And this is quite an interesting field of research. Hossenfelder will tell you this. The idea is that we want to reciprocally connect our quantum gravity theories to empirical results and empirical results to our quantum gravity theories by building models. And they do go either way. So you can kind of start at the results and kind of work back towards our theories. Or you can start with particular theories like doing loop quantum gravity phenomenology and trying to build a model that's going to be able to kind of reach up. So you can see this is really quite a challenging field to be in. Not all of it is supposed to be particular to quantum gravity approaches, but could be a general constraint on any of them, such as this Lorentz invariance. This is the main result that's come out from this. They've found very tight constraints on any observable violations of Lorentz invariance. So trying all these different ways to try and find if this could be broken, and there's no, they've got it down to where you can expect to find it, and that window keeps getting smaller and smaller, if it is indeed going to happen, which obviously causes difficulties for approaches that have discrete space-time violating Lorentz invariance. Yeah, so I think this quantum gravity phenomenology, it really links up to philosophy of science, general philosophy of science, where there's a lot on model buildings and modeling in science. This is a really important field of philosophy of science, but no one's really looked at quantum gravity phenomenology yet as philosophers. So if you're looking for a project, I think this could be an interesting project. And yeah, this QG phenomenology can also link us up to tabletop experiments, so things that you could possibly build in the laboratory. And these are currently quite active. You can see this book called Quantum Gravity in a Laboratory. It's a short one, again, for Cambridge Elements, by Nick Huggard, Neil Zimmerman, and Mike Schneider, talking about these tabletop experiments. I'm not going to say more about them now, but quite exciting again. And another example of such a tabletop experiment, of course, are these analog black holes, which I'm obliged to mention as well, an upcoming workshop in Urbino, if you'd like to learn more about these, building quantum black holes in your lab, right? So this is quite exciting as well, to help us get, actual empirical results that we can use to constrain our theories. And as I said, there's other empirical motivations. These ones on the side here are the ones that are related to the empirical motivations. Any questions, comments? Yes?
One that just briefly came up methodologically. Did you get all of those out of just reading stuff or also talking to people?
Yeah, mostly reading stuff. I think.
And have you looked at kind of distribution of like what does everyone manage? Or is it like there's some that are just to be found once or twice? Like how?
Yeah, I haven't looked at that. That would be a good question.
Like where do you say is everyone's what are most people like really driven by?
Yeah, what most people are really driven by, I would say definitely the cosmology. I think these ones are definitely less, like the measurement problem is not motivating too many people, except like Penrose. The black hole thermodynamics, of course, and I think unification, singularity resolution, really big one. So I think, these ones over here are probably the ones that are more motivational than these ones, apart from that. Yeah, and unification as well, I think. So I'm gonna, if I have time, come back to quantization, and tomorrow I'll be discussing the singularity resolution. Yeah.
Just a small comment on the part of the dark term. So, if I remember correctly, you mentioned that it is not actually bringing us to look for a theory of quantum gravity or a different theory in general, but I think there is a reason for that. So, for example, We know that there is modified Newtonian dynamics, so this alternative theory that purports to account for the same phenomena without dark matter, but we also know that to some extent it's not as functional as the standard model of cosmology. So the point is, by admitting dark matter, we are still doing pretty well in establishing many functional phenomena, relationships among phenomena. So I think it's a different kind of reason why we are not looking for a new theory, because even if we don't know what it is, we are doing very well with it, while other theories are not really giving us an indication how to proceed. So I think this is an interesting contrast.
Yeah, but then it could still be kind of...
Dark energy is different.
Yeah, exactly. So, yeah, I guess you can push it, and as long as you're getting interesting stuff coming out, then you don't kind of need to look for quantum gravity, which is much harder in a way, right? Yeah, so that's fair, that's fair. We've got other means that are a bit easier to deal with and motivating. Cool. All right, so moving now to this primary motivation, which, as I said, I think is the primary motivation, which is going to give us the minimal characterization of quantum gravity. So I think it's this, that we're searching for a new theory of fundamental physics that describes the domains where both GR and QFT are thought to be necessary, and which somehow combines or takes into account the lessons of both these frameworks. So this, I think, is what all the approaches agree upon, and I think it's safe to say if they're not doing this, they're not doing quantum gravity. But this, although it's kind of what I think is the status quo, I think it can be questioned, it should be questioned. We're philosophers, let's do some pushing here. And I think it's mainly based on this desire for external consistency between these two frameworks. We want a single coherent picture of the world. So, yeah, probably I don't need to go over this to show kind of the two frameworks and where they conflict. The main thing, to do with quantization, space-time dynamical versus non-dynamical. They're both supposed to be universal theories, and yet typically we can usually get away with using one or the other. But the fact that they are both universal theories, there's a conflict there. So obviously this needs to be filled in more. In particular, what do I mean by describes? What are the domains where this theory is necessary? And what do I mean by combines or takes into account? There's different ways of doing this too. So I'll say a little bit about each of these 3 points. Starting with the domains. Where do we need quantum gravity? So of course we have a theory that combines GR and QFT. This is what Wallace calls low energy quantum gravity. Basically it's semi-classical gravity plus a treatment of the quantum fluctuations using this background field method. But the problem is this theory, it's a theory that combines our two frameworks, but it breaks down around the Planck scale. And so it seems like this breakdown might be a symptom of the external inconsistencies between the two frameworks. Nevertheless, this doesn't prevent us from using it in domains where it is predictive, right? The theory, people say that it's not consistent, but it is consistent just as long as you're restricting it to a particular domain. So that domain where it is consistent, that's fine, but the domains where we need the new theory of quantum gravity is going to be beyond this. So it will need to describe the Planck scale where this one breaks down. But as we've argued, quantum gravity, it needs to describe the Planck scale. It doesn't need to be valid to arbitrarily high energies. So it can break down somewhere else. But at the very least, it should describe the Planck scale. So quantum gravity usually gets treated as a fundamental theory, in which case you would be motivated that it applies to arbitrarily high energy scales. But we needn't take quantum gravity to be a final fundamental theory, right? Then it might just be a stepping stone towards a fundamental theory. So in order to satisfy this primary motivation, I think the domains just need to, include the Planck scale as well as inside black holes and the early universe. Does that make sense? Okay. So yeah, if we just want a theory that satisfies the primary motivation, this is putting some restrictions on it and showing, what's necessary and what's kind of asking for more. I feel like you're asking for more if you're asking for a final theory that's valid, really high energies. Not that that's not already really high energies, but okay. So next up, we want our theory to actually describe these domains. But what do we mean by describe? This is a bit tricky, right? So ideally, what we mean is that a theory describes a particular domain if it's giving us predictions in that domain that we've tested and they haven't been falsified. This is challenging in the case of, the Planck scale and very early universe. So more minimally, we want the theory to be at least formally predictive, that it's giving us some answers, even if we haven't yet been able to figure out how to test these answers. And of course, as I said, having these empirical constraints upon it, including via the correspondence relations with our current theories. So maybe you can think more about this, how we could develop, how could quantum gravity describe our world, right? But I think this is at least a first start there. So the final part is this idea of combining or taking into account the lessons of both GR and quantum theory. And here, I think there are different ways of doing it. So I think there's ways that are necessary and ways which just kind of are sufficient. So I would say, I was reading this Ashketar paper, and he puts it like this. Everything in our past experience tells us that the two descriptions of nature we currently use must be approximations, special cases which arise as suitable limits of a single universal theory. That theory must be based on a synthesis of the basic principles of general relativity and quantum mechanics. And this would be the quantum theory of gravity that we're looking for. So it's really talking about this synthesis of principles of both theories. So from this, I think we can read out the two necessary conditions. Firstly, that this new theory is going to recover both of our theories in their domains of applicability, which is up here, the special cases which arise as suitable limits of this theory. And second, that it combines the principles of both theories. So I think here, when he's saying synthesis of principles, I think it's a bit misleading because I read that as like, all right, it's synthesizing these principles into some sort of new principles. But it needn't be that, and it's less likely to be that, I think, because that's quite challenging. Rather, it's just that the theory could feature some principles from GR and some principles from quantum theory. You choose, pick and choose. Some of them, at least it's got one from each theory. And typically, the principle from GR taken is background independence. People like this one will get motivated by this. For quantum mechanics, it's quantization. So now I think there's two ways of kind of satisfying this take into account, which first one I'm calling the new framework perspective, which you can see a bit. So yeah, Ashita, he's quite, I think he's a bit ambiguous between which of these frameworks he means. When I was reading him, I couldn't work out. So these two ones that I'm presenting, the new framework versus the standard account, they're not coming from him, they're not his terms, but I've been inspired by reading his papers to see these two different ways of viewing it. So on this new framework perspective, we need to recover both GR and quantum theory, because, as he says, they're each understood as a distinct body of universal rules. And he thinks because of this, the quantization of gravity is essentially different from quantizing the electromagnetic field. So here he's saying, in the paper with Girac, from this viewpoint, the problem is to obtain a new body of rules which suitably encompasses the essential features of those of quantum mechanics and general relativity. So here, it seems like we need a new framework that's more fundamental than both quantum and gravity. And some other motivations, I would say, is the measurement problem, reasons for not taking quantum as fundamental. Other reasons might be problems with semi-classical gravity, or things that we see as inadequate responses to black hole information loss. So this is motivation for Oppenheim's approach, which again is supposed to modify both gravity and quantum theory. So in that sense, it's a new framework. On the other hand, we have the standard perspective, which is what most people are taking, which is treating quantum mechanics as fundamental. And because quantum mechanics is fundamental and being used in your quantum theory of gravity, you don't need to recover it. It's already built in. You've got a quantum theory already. So not seeking to modify quantum theory. So it's really treating quantum theory as universal and fundamental and not going to be drastically modified. So this is very popular. Yeah, this paper by Lowell, I found a lot in that one. I forgot what it was called now. Quantum Gravity in 20 Questions, something like this, and they go through. And they say the physical world at the fundamental level is governed by quantum laws. And the classical picture is only an approximation valid at sufficiently low energies and sufficiently large scales. And this very standard motivation that you'll hear a lot of people saying, quantum mechanics says that all dynamical fields should be quantized. GR says that spacetime is a dynamical field, therefore spacetime should be quantized. And this is really the main picture that most people are taking. So you can see how it's in contrast with this new framework, which is saying that both of our theories are approximations. This one's just saying, oh, no, quantum is fundamental, but GR is the approximation. So questions on this?
You know some who say thermodynamics is fundamental, or electrodynamics, or is fundamental also meant in a smallest way, that smallest is the most fundamental?
Yeah. I think this is a really good question about fundamentality. So I would say fundamental, we're meaning that it's a broader theory and that it's encompassing the other theories. And a reason why I think these particle physics are taking kind of the particles, although they're smaller, they're also more fundamental in this other sense that it's a more encompassing theory for quantum field theory, including special relativity is more encompassing than plain quantum mechanics, for instance, as a framework. So yeah, I don't have in mind about the kind of building block picture, but of course that does apply in quantum gravity as well, right? Because we're looking kind of for the building blocks of space-time that are non-spatiotemporal in some sense. Though even that might be another assumption that seems to already go beyond the primary motivation I just said, doesn't it? Other comment?
My question maybe is trivial, so I don't know. But we are assuming that for quantum gravity, so we will have theory describing the universe at every scale, right? So we want a theory with combined GR and quantum mechanics. But why are we assuming that quantum mechanics is the right amount of theory to describe physics? So in the regimes where we know that fits, because okay, we have the QCT, which is trivial in the beginning, and all the other theories we don't know.
Yeah.
So why are we assuming that the theory of quantum gravity should be quantum?
Yeah, thanks. I love it. Yes.
Gravity, so
Yes.
is quantum.
Yeah, exactly. Yeah, exactly. I completely agree. I think this is exactly what I'm trying to get at. You know, why are we assuming this? And it seems like, these sorts of motivations, they're just kind of taking it as fundamental. I think I asked Carlo about this. I'm like, why? And he's like, oh, you know, it's also just really hard. We can't imagine something beyond quantum. And also, so started thinking about this with one of my PhD students who's thinking there are aspects of quantum mechanics which couldn't kind of disappear and then get recovered, such as non-locality or entanglement, I would say. So maybe there's aspects that get retained, but not the whole framework. So I think this is a project, you know. And another project would be kind of this kind of, I've forgotten what they call it, the axiomatic approaches to find the axioms to build up quantum theory, quantum information theory. I think that's an interesting project too, as a stepping stone towards finding how we could recover quantum mechanics. Cool. So this very classic paper from Butterfield and Isham, where they're saying there are 4 different ways to approach quantum gravity. We can quantize GR, we can get GR as the low energy limit of a different quantum theory that has been obtained by quantization, or GR as the low energy limit of quantization of a theory that is not a quantization of classical theory, or start ab initio with a new theory. So on this classification, I'd say these top two represent standard perspective, what I've called the standard perspective. This one obviously represents the new framework perspective, and this middle one I think could be either, depending on whether or not you formulate it in the framework of quantum theory as currently understood, or whether you're modifying quantum theory in some way. But as we've seen, the dominant approach is really number 1, where not only is quantum gravity supposed to be a quantum theory, but it's supposed to be one in which gravity is quantized. And yeah, you mentioned thermodynamics. I think this is also really interesting. And why is this? It's only now kind of starting to be recognized, hey, why don't we take this into our definition, right? We're talking about unifying or taking into account these two, GR and quantum theory. But why not thermodynamics as well? Why isn't that also a fundamental theory? And I think we should be looking at this. So there's different kind of approaches looking at this as well. So Jacobson, of course, these emergent gravity approaches I think are really cool. I I might have some slides of those, but I'm probably running out of time. But basically, these ones being motivated by kind of condensed matter physics or hydrodynamics, taking space-time as an emergent phenomenon, akin to hydrodynamics. The main thing is that if you quantize that, you will end up with quasi-particles, phonons. You won't be getting at the actual fundamental atoms of space-time. I'll come back to it. But these are kind of options towards this new framework perspective, I would say. Okay, so that's the summary so far. I've been looking for motivations to kind of better understand why we're looking for this theory of quantum gravity. Once we figure out these motivations, to frame them as principles, and then kind of question them, evaluate, are they well motivated? What's the consequences of keeping them or dropping them? I've presented the primary motivation as kind of this minimal definition. And I think we can look more closely at each of the other motivations, the ones in the big list, seeing whether they should function as constraints or should they be in other roles like the heuristic roles. And you see many of those ones with the pink arrows towards them, they're being motivated already from the primary motivation. So you're kind of starting with that, but it also goes the other way, that your other motivations motivate you towards a theory that satisfies this primary one. And yeah, I think what comes out from this already is this question, is quantum fundamental? What about this new framework perspective? Could we be looking at this a bit more seriously? Yeah. Comments?
I mean, if you spend so much time looking at this, I'd be curious, during your research, were there any motivations or any things that really surprised you, where you were like, okay, that's, because you said you were forced or kind of led towards this inquiry based on this comment you got on a paper proposal where you wrote on gravity, but there wasn't, the definition was missing, so I'm just curious, like, did many new things come up while doing that, and were you surprised that, wow, that's a motivation for someone, that's quite interesting?
Oh, yeah. That's a good question. Not really. Do I have the map up? I don't know where I put the map again. Maybe that's a question for you guys. Like, what do you find as the most interesting motivations here? Are there any that surprise you?
I mean, I guess I was asking because there wasn't anything that surprised you.
Yeah.
So I was curious if you found anything where you were saying, okay, wow, that's strange or that's weird. Not so much.
No, not so much.
Physicists are boring.
Yeah, I think they are a bit boring. Yeah. I mean, I guess it's more interesting to say kind of why, but then again, it comes back to them being boring. Like, why are so few people being motivated by measurement problem? Why is it just Penrose doing this and people are not taking him seriously? It does seem this kind of ingrained kind of dominance or assumption that quantum is really fundamental, right? And that this kind of problem is not to be solved by developing a new theory, but by developing interpretations of the theory. So I think that's pretty strange. Yeah, please.
You mentioned Berlin on one of the slides. So he is at my university and he taught me QFT. But I was wondering, because his theory of emergent gravity can explain the flattening of rotation curves and also dark energy. But how does this relate to quantum gravity?
Yeah, so I think it's a step towards quantum gravity. Oh, you mean whether it satisfies this one, right? The primary motivation. If it does, then we would class it as quantum gravity, I guess.
Okay.
Yeah.
I'm sure if it does it.
Yeah. I can't think off the top of my head either.
So, but would you say that considering thermodynamics as fundamental could be a step towards that primary motivation as well?
Yeah,
How is
so
that related?
yeah, exactly. So I think this is a motivation. Oh man, how many times do I say motivation? For reconsidering this primary motivation. You know, I'm not putting it forward as something to be non-question. Maybe we can modify it. Maybe a better approach is to reframe it as including thermodynamics as well, and change some of the other what do you call it? Stuff in that, and get a new understanding of what quantum gravity is supposed to be. Or I guess if we are taking this as really the definition of quantum gravity, we could just say, well, maybe looking for a theory that quantum gravity is just wrong and we should be looking along these lines, get a whole new definition for a new type of theory. And maybe that's a bit more along the lines where we should be going. Yeah, it's a really interesting question. Yes, please.
Can you go back to the last slide that you had?
The summary?
Please, yes. I think maybe you had the discussion here and I just kind of missed it a little bit, but just we were talking about like a new framework and like this idea of like recovery. I was just wondering if you could say something like general about what you mean. Like, do you mean formally derived, to like have the same theoretical posits show up? General explanation, like what's the benchmark, I guess, for like when this would be like good enough to feel like we were getting something?
Yeah, I love this question. I've always been super fascinated by this kind of correspondence principle, especially for quantum gravity, that people are taking this as the main constraint on it. But it is not well worked out. So I think, yeah, exactly the way you framed it was getting at the problem. I think what we normally do is that we develop these kind of links, any sort of links. They don't even have to be kind of derivations, just like linking of principles. Stefan Hartmann has a nice paper, the different types of correspondences that we might have. Like, it's just that the two theories agree on some things, that's a correspondence. So it's not necessarily a derivation, but usually physicists are thinking about, limiting relations and derivations there. But I think even those, of course, they're very hand-wavy, they're very approximate. It's like, we get the idea of how it could happen. And I think that's exactly what goes on. You show that there are a lot of these different correspondences, and then at some point you've shown enough that you become satisfied, like, okay, it's there. But that's exactly what you're asking, like, at what point do we become satisfied? And I think that's a really interesting question. Stefan Hartmann on correspondence. Yeah. Please.
I'm on one more motivation, maybe, because one might ask obviously, why are we looking for a quantum gravity theory if our perturbative quantum gravity is the best effective theory we have? The cutoff is very, very high. So one might ask why? And I guess because some people think that a quantum gravity theory might be necessary to have, in general, a theory of everything. So, because I guess people might say, why, if all the other quantum field theories are worse than perturbative quantum gravity, why are we looking for quantum gravity?
Yeah. I think this is nice. So it's definitely a theory that satisfies like this primary motivation, depending on the domains, right? If it's going to break down and not be formally predictive at the Planck scale, then it's not going to do it for us. But if it is, then boom, you've got it. You've satisfied this primary motivation. And yet exactly this, a lot of people are not satisfied with it, right? They want something else. So then I think the onus is on them to really say, well, what's wrong with it? What is driving you? And then you can get more conditions, For the next part, I was going to say a little bit about quantization, because obviously this standard perspective and what we just saw with the Butterfield and Isham paper, people are taking quantization, quantum gravity should be a quantization of GR. And then, if we have time, I'll say a little bit about unification, because I think unification is quite interesting. So, of course, as you're familiar, quantization is kind of the recipe from which we can construct a quantum theory from a classical one. And historically, the different approaches to quantum gravity get classified by the ways which they do this. So, first being covariant quantization, where we're trying to treat gravity in the framework like the other forces in quantum field theory. String theory is being the main example that historically came out of this. And it's really using this high energy physics perspective. I'm not sure, did Eric go over this yesterday already, or is it familiar or not? No? Oh, okay. So yeah, basically here what you do is, as we heard, using perturbation theory in quantum field theory. So you have your space-time metric, and you split it into a background plus a little fluctuation, and then you quantize these fluctuations while the background is classical and non-dynamical. And this approach, the perturbative approach, which was the original one, really suffers from the non-renormalizability of gravity. This means, very basically, that it's not going to give you predictions. It blows up and becomes quite infinite. You'll need a kind of infinite number of parameters to set to get answers from this theory. So you can't get answers from this theory. In response, some non-perturbative means were developed. The main one being this asymptotic safety scenario, which is inspired by quantum chromodynamics, which has this asymptotically free fixed point. So maybe, I always get this like hard to say, the idea that gravity, although perturbatively is non-renormalizable, maybe non-perturbatively it's renormalizable. So if that is the case, and we don't know, it's a hypothesis, if this is the case, then the coupling flows to a fixed point and it won't go to infinity. So if this works, then you'll have a theory of quantum gravity that satisfies our primary motivation, but maybe non-satisfactory for other reasons that go beyond the primary motivation. And like every approach, there's problems with it too. It may suffer from a problem of unitarity if it conflicts with unitarity. But of course, people are working on this. The next way of quantization is Feynman quantization. So basically, you get this gravitational path integral, and then you want to solve it. So ways of doing this: causal dynamical triangulation. So they want to get an approximation to this using little triangles, like what's pyramids? So it's a way of calculating this, but it doesn't say too much about the ontology of quantum gravity. Causal set theory is another approach which uses these techniques. And the third way of classifying these approaches in terms of quantization is, of course, the canonical quantization. So whereas the covariant one was taken by the high energy kind of particle physicists who, as I said, it involves kind of keeping a background and talking about perturbations on the background or quantum fluctuations on the background. It gets challenged by people who think, no, we should be preserving background independence as a principle. So those who kind of coming from the GR side prefer the canonical quantization approach. So you use the different recipe, but this recipe involves splitting space-time into space and time. And then you have to kind of put them back together, of course. So you're quantizing it, and then, yeah, that's your goal. So this one aims to preserve the principle of background independence. But these canonical approaches historically are known for suffering this problem of time. So you're getting an equation when time seems to fall out. It's supposed to be your dynamical equation, but where's the dynamics, basically? So this problem of time is a big problem. And the main example of this style of approach that's been developed is, of course, loop quantum gravity. So different ways of quantizing give you different families of approaches, but there are other approaches that are not quantization approaches. So these hybrid accounts, such as semi-classical gravity or that low energy quantum gravity I mentioned. So this is basically keeping space-time classical, but matter as quantum, and then trying to couple those together. So you're not quantizing space-time here. And then, as I said, there's these emergent gravity approaches, which are really quite eclectic. And I don't have too many slides on these. They're really inspired more by condensed matter. We're treating gravity as hydrodynamics, which is quite interesting. But what they do agree upon is that, yes, quantizing. We're not going to... They tell us that quantizing gravity is just the wrong way of getting a more fundamental theory. And these were the examples there. So one example of this is emergent space-time from fluids, so analog gravity approaches. So if you imagine here you have your quantum fluid, or even a classical fluid, water. You can talk about expanding it in this way. So small density perturbations, small, what was the other one? Coherent phase fluctuations. And then you can basically work it out that you have. How do I move this? You'll get this new Lagrangian, which is kind of in two parts. One describing your ground state of the fluid, so the surface of the fluid, which itself you can think of as a space-time. But what you also get is like vibrations of this fluid creates this kind of effective metric that's emerged from it. So it's just coming as a real generic feature of this linearization process. So it's quite easy to get these models out. And what you end up is this effective Lagrangian is formally identical to that of a massless scalar field in 3+1 dimension space-time with a curved effective metric. So you could have your water and then this kind of extra space-time that's come out of it. So this is quite cool. And of course, when you quantize this, so you can think of it as like coming out from vibrations of your water. You quantize that. What do you get when you're quantizing these vibrations? You're getting phonons, sound particles. It's not giving you, so you're getting these quanta, but they're not kind of real, right? They're effective. So they're real at some level, but this effective theory, when you push it to higher energy and figure out kind of what's going on underneath it, it's going to break down. And it breaks down when it reaches the scales of, this. So once you can detect kind of the atomic spacings between your water molecules or particles, then your theory is not going to give you this effective space-time anymore. It's broken down. And this is the one, if you've heard of the dumb holes, again, promoting this meeting coming up. UNRWA had this idea of using them if we have, imagine a waterfall, and the water is going off a cliff. At some point, the speed of the water is faster than your local speed of sound. So that's happening here. And you've got one fishy up here, and you've got another fishy down here, but they're special fish, they have ears. The one that's fallen down is screaming, "Help me, help me." But because the water here is going faster than the local speed of sound, that's not going to be able to reach his friend at the top. So you've produced what's called a dumb hole horizon, analogous to a black hole, where you can see, they're calling it dumb as being mute, it can't speak. That's what it's meant. Like when you say deaf and dumb, this is what is meant by dumb. And as you can see, you can actually set these up that the horizon is described by the same equations that we use to describe black holes, doing the same sort of thing, getting these fluctuations over the fixed background. And then you can work out that they actually have the same form as a Schwarzschild black hole. So this is very interesting. It's a way of thinking about emergent space-time. But it's kind of showing that quantization is not the way to go. It's not going to give you this more fundamental theory if you, by analogy, looking for a theory that's going to describe what's going on underneath, like the particles of the water being analogous to whatever we take to be the atoms of space-time. Quantization isn't going to get you that. So yeah, as I said, you can learn more about these analog models in September here in Urbino, especially whether they can be useful for teaching us about Hawking radiation, which we're taking as being one of our best guides towards understanding black hole thermodynamics. Okay. So were there questions on, that was really quick, but on quantization, things like this?
Sorry, before we follow, we were trying to explain that it didn't have to, with the waterfall example,
Oh, yeah.
we didn't have to quantize.
We quantize it, but the quantization will just give you non-fundamental quanta. You'll get quanta of this effective space-time and not quanta of the underlying fluid, is the idea. But on these models, as you can see, right, it's space-time. It's a curved space-time emerging from a flat space-time. So it's space-time emergent from space-time. So is it a quantum gravity approach or not? It's more like inspiring towards a quantum gravity approach, saying it could be along these lines.
Okay. And so the quantization, it's okay. I'll ask you after this.
Okay, no worries. Yeah, basically, yeah, you're quantizing the fluctuations is the idea, and not kind of the background, if that helps.
So there's still quantization.
Yeah, this is still but it's showing that the quantization, if you do it, isn't going to give you quantum gravity as a more fundamental theory. If we're taking quantum gravity as being, kind of the atoms of space-time. It's supposed to build us space-time. It's not giving us those constituents.
Yeah, okay. So it's not quantum gravity, but it still explain. It will still be able to explain black hole.
Yes, exactly. Yeah. Yep. Yeah. So it's really interesting for exploring the possible mechanisms of Hawking radiation, especially Hawking radiation using quantum field theory in curved space-time, right? So not a full theory of quantum gravity yet. It's like a step towards it. So, yes, please.
Yeah, just a clarification, because by the way you're using quantizing quantization here, I guess you can mean that we introduce a theory which describes a certain system as a quantum system, right?
Mm-hmm.
Though I was wondering, there are also some approaches which are considered quantum gravitational approaches, broad label, that will use quantization not to produce a quantum system, like a quantum description of space-time, but rather more as a heuristical formal device.
Yeah.
In which case you must have a structure which is non-classical in the sense it's not general relativistic, but its physical interpretation is a bit more tricky. So mathematically, it will use, for example, deformation quantization, but actually, when you start interpreting the formalism, it's unclear if it has superpositions and so on. So, would you consider in that case? So, would you say that we can subsume these kinds of areas, these kinds of theories here, non-classical theories, in a sense, under the same label, or there might be something different going on with the primary motivation and the standard versus group framework perspectives you mentioned before?
Yeah, exactly. Good question. So are we taking these as approaches to quantum gravity, right? And does it fit with this motivation, or is it more like a stepping stone towards it?
Yeah, because so a couple of these approaches, for example, some community spacetime approaches, are usually taken at the very least to describe spatial physics near the Planck length or immediately beyond the Planck length. So in that sense, it would fall into the domain we are talking about, and it would be non-classical in the sense that it's general relativistic, though it does not necessarily mean that the system being described, in this case spatial structure, is quantum. So we're sure if there is entanglement there, or have some non-classical effects, whether they are the superpositions.
Yeah.
So,
But do we get emergent quantumness from it, or we're just kind of using the quantumness, I guess?
We can reconstruct quantum field theory from that, and in this case, we're assuming that highly energetic quantum fields will behave also differently at the relevant scale because of the coupling that, of course, the background structure,
Yeah, exactly. So it is reminding me a bit perhaps like this asymptotic safety approach, where it is satisfying our conditions, and yet it's not taken to be the theory of quantum gravity. Nevertheless, these predictions that it's giving us and the indications are supposed to be those that will come from the quantum gravity theory. So if we are looking for a deeper theory than this, if we're not satisfied with these, we need to say again why we're not satisfied with them. And also, they're definitely useful. They're giving us predictions that we expect will also be reproduced by a theory of quantum gravity beyond that, if we want one beyond that. Yeah, that's a really good point, thanks. That's clarifying. Okay, so it seems like we've got lots of other options. We might not need to quantize, as we said here. There's different possibilities. So the motivations for quantization, you can see they can come from, if we're thinking there's inconsistencies, by having quantum matter with classical space-time. This is a big motivation. Many people think this is just not consistent. If we're interested in unification, it depends kind of, is this a real unification? If we're just quantizing GR, you're getting that minimal sense of unification, I said, where they treated all forces in a single framework, but it's not unification in the sense that they're being treated as the same, coming from the same one object in a way. So it's a sense of unification, but it's a minimal sense of unification. Singularity resolution, well, one way of getting rid of singularities, if they're coming, for instance, from pushing the theory too hard and infinities pop out, that's your singularity. Well, one way of getting rid of that is just having a discrete structure to space-time, or another way of getting a minimal length, so it doesn't go to infinity anymore. And we can do that through quantization, where we get kind of, quanta of space-time. So that's a motivation as well. So I think it's interesting then to look into those. So I think these are some motivations for quantization, and I think none of them are really compelling, really. So we have these heuristic arguments and thought experiments. I'll say a little bit about these. The space-time singularities we'll discuss more tomorrow. This universality of quantum theory, that motivation I mentioned, that, if we're trying to put our theories together, then it's telling us we need quantization of space-time as a dynamical field. Unification I just mentioned, and UV completion as well, similar to what I just said for the singularities. If your theory just kind of says there is a minimal length or a highest energy you can reach, then your theory has described all highest energies. So it's UV complete, but it's not the only way of getting a UV complete theory. So basically, none of these really conclusively demonstrate that we need to quantize gravity. At the end of the day, we should look at experiments and observations, and only that can motivate us. Are you telling me to wrap up? What's going on? Oh, okay. Just tell me when I need to wrap up. So I think this is quite interesting. This paper is by Oppenheim. So he's saying, is it time to rethink quantum gravity? And there's many of these, oh man, do I have, I thought I had another slide. This one, yeah. So these thought experiments, this is what most people will appeal to. So it's this idea that if we have something that's quantum and we're putting it with something that's non-quantum, then the quantumness is going to infect the non-quantum thing, and it's going to be quantum. It's going to fall into a superposition along with it. And there's no way of stopping this. Quantumness is going out there infecting everything, right? So yeah, especially the uncertainty relations kind of infect the classical system. So these sort of arguments, and there's many different arguments. Feynman has an argument, Bohr and Rosenfeld had an argument for these. And again, I think they're heuristically very powerful, but, as with other no-go theorems, you could always find ways to evade them. So this one, imagine you have this double slit experiment with a massive particle. Here he's got a cannonball. So you have your particle, and if it's got a classical gravitational field, then you will be able to measure this gravitational field without disturbing your particle. So you can use your little, what's this called, pendulum, to detect the gravitational field. And from that, you'll be able to tell which slit your particle went through, which is obviously in violation with the experiment. If we're able to tell which slit it's gone through, then we're not getting this interference pattern anymore in contradiction with the experiment. So this is an argument for why the gravitational field needs to also be quantum in order to preserve the experiment. So the idea is that, yeah, just having gravity as non-quantum is going to conflict. So therefore, it must be. To preserve the superpositions, it also has to be quantum. So this is kind of the general flavor. And Oppenheim is motivated by these to say, well, there's other ways we can explain this. We can get away from it by modifying both quantum theory and gravity. So he's got a semi-classical approach, or like a hybrid approach, but is modifying both theories. Don't ask me too much about it because I haven't looked into it yet. But basically the key is that he's putting some randomness into the gravitational field, but not quantumness, I think is the way. And that will help us avoid this and give us the interference patterns. And he's shown that it reduces to GR in the classical limit, and that it also has some other nice features, such as solving the information loss problem and the measurement problem. So it's one way of showing that we might not need to quantize gravity. The singularities I'll do tomorrow. I just wanted to finish by saying about, maybe this universality of quantum theory, because this comes up so much. I think this is what physicists always say. So Adlam, she's argued that actually, even if we're taking quantum theory as fundamental, and therefore that it seems like we need to quantize gravity, because quantum theory tells us that every dynamical field needs to be quantized, and gravity is a dynamical field according to GR. She says it still might not compel us to quantize gravity. It might actually depend on what interpretation of quantum mechanics you're working with. So, for instance, the psi-incomplete interpretations might be compatible. So, if the relevant notion of unification here is that there should ultimately be only one type of stuff, quantum stuff, and therefore, since ordinary matter gravitates and ordinary matter is assumed to be composed entirely of quantum stuff, it follows that quantum stuff must gravitate. But not all interpretations of quantum mechanics agree that there exists only quantum stuff. So quantum mechanics interpretations can differ on this. So I think that's quite interesting. And yeah, I'll just finish by saying something about unification again, because I think this is also, I'm going to look into this more. I think this is going to be the next book on unification, maybe. Because we have, this kind of history of physics, it's a bit fuzzy, but we tend to view it as a history of unifications, and that we're making progress always by unifying and by pointing to more unified theories. And then it seems like quantum gravity is going to be this kind of ultimate unified theory. So I'm just, curious about this and where this kind of idea has come from. I'm starting to think maybe it even goes back to like the ancient Greeks and this idea that all the universe must be one, some fundamental oneness, which would be quite a nice idea, right? Because physics and philosophy came out from these ancient Greek ideas, and maybe we've just got this kind of inheritance from them, simplicity and beauty. So that's definitely something to look at. But also just to emphasize again, although quantization might be one way of kind of coming towards a unified theory, it's not going to be like the deep sense of unification where you get this oneness. Okay, so I think I might leave it there. Any final question? Yeah.
Just a general question. Given all the constraints that you outlined, specifically the general correspondence, I was just wondering, what do you think is given the current landscape.
I don't know. Yeah, I'm a bit skeptical of all of them, honestly. But also, I haven't really, as I said, I haven't really gone through and started to evaluate them based on these different criteria either. That's kind of the second and third step of this. Yeah. But I think, yeah, it does kind of motivate us more, one, to look at these kind of more quirky approaches, like the emergent gravity ones, but also it might make us think more about the really non-quirky approaches, such as asymptotic safety. Like, why are people not satisfied with that? You know, if we're able to get it predictive at the Planck scale and it's combined of theories, what more do you want? So I think that's really interesting. It's opening up new avenues to look into other than kind of the standard focus on string theory and loop quantum gravity. Thanks.